Hello everyone. So today I'm going to continue um, solving this example that we brought up in the last lecture. So the next thing I'm going to do that now we have these uh, ODEs that we defined, and this is the general one that we defined last time, right? And let me see. And then we applied the boundary conditions. So this is the general equation we had, and then we apply the boundary conditions to find the equation for I equals to 2 and I equals to n, right? So yeah, so we have three equations. This is n I equals to 3 to n minus 1. And this is the equation for I equals to 2, and this is the equation for I equals to n. So the next thing I'm going to do is I'm going to take these equations and try to constitute a matrix. So let me see. And by constituting a matrix, I mean that I will combine all of them into a matrix form, so then we can simply represent it even like in computer programs, and then make a matrix and solve the resulting matrix. Okay, so the next step is constitute a matrix. So the matrix that I'm gonna create, it looks like this. So let me start that. This is the first one. This is the main matrix. Then we have this component, and finally the forcing component. Okay, so let me get started. So the first one is d over du over dt term. So these equations, right? And this is gonna be from u2, u3 to until un, correct? And then here we have the same thing. So this is u2, u3, un minus 1, and un. So let me just clean here a little bit. un minus 1 and un equals to, so this is plus, equals to the right hand side. So I'm just using these terms, okay? So let's see what is the first one. The first one is from the first equation that we had, which is I equals to 2, and that is this one, okay? So in the left hand side, we only have du2 over dt plus b2u2 c2u3 equals to f2. On the right hand side, we are going to have f2 minus a2 u left. So let me just first write the right hand side, because this is the simplest and clearer, the most clear one. f2 minus a2 u left. Okay, so this is the left hand side of the first equation, and then the terms is b2 u2. So I have B2 here, and then C2 U3. So I have C2 here, and the rest of the terms are just 0. Okay. So let's look at the second equation. So the second equation is going to come from here. So we have du3 over dt a3u2 b3 u3 c3 u4. So I have du3 here over dt plus the next term is going to be a3 u2 b3 u3 and c3 u4. Okay, and then the next terms are going to be 0. And we will have the same thing until un. So for un, I'm going to have cn minus 1 un. So it's going to be here, cn minus 1. And then I have bn minus 1 here. And then I have an minus 1 here. Okay. And this equals to f3 here, and then is equals to fn here. So I'm gonna just have the same thing up to fn minus 1 here. I'm gonna just have the same thing up to here. Okay. And the way this is gonna work is, and let me just do the last equation. So the last equation, we have this equation. So the right hand side is just fn, so I'm just gonna write it down, fn. The left hand side, dun over dt, which we already have, and here, which we already have, and here the only change is we don't have any term for un plus 1, which is a ghost term, a ghost cell, and the only change is we have to change the coefficient for un minus 1, and that's it, and the rest are going to be the same. So we have here bn, and instead of an, I'm going to have an plus cn for un minus 1. So here I'm going to have an minus an plus cn for the last term, and this one is going to be 0. Okay. So if I want, and this one is going to be 0 to here. So if I want to show it, it's going to be something like this. So this is the diagonal. We only have the terms in the diagonal of this matrix. The same thing for this one. And the same thing for this one. So let me do it again. So this one goes here because I want to show the last term too. This is the diagonal of this matrix. And then this term is like this. Let me change it a little bit so you get it better here. So this is an plus 1. So I'm gonna have it here. It's gonna be an minus 1. And so this is the kind of the architecture of these this matrix. Okay, so this is how it looks like, and the rest of the terms here are all 0. So here is just zeros, and here also is zeros. And the only non-zero parameters are just the ones on this diagonal that I showed, okay, in these 3 lines, in this line, and this line. Okay, and the rest of the terms for this matrix are just 0. So this is the matrix representation of this set of equations that we had, and we discretize in space, okay? And so let me, in order to make it simpler, I want to define this as a vector u. So I define this as vector u, because this is a vector. I define this as vector f, and define this as a matrix A. Okay. And write the original equation that we had as this. The whole equation is going to be as du over dt, the whole set of discretized equations, plus a times u equals to f. Okay. So this is a matrix representation of this system, and so these are just set of ODEs, ordinary differential equations, in time, and we call this semi-discrete system. What does this mean, semi-discrete? It is discretized only in space, so that is why we call it semi-discrete system. If you notice, it is not yet been discretized in time, which is this term, right? And we need to also do that. So that is why we call this a semi-discrete system, where we have discretized it in space. So if you look at the original equation that we had, just for you to remember, was this. And we converted that equation to this semi-discrete system, which is shown here, where A is this matrix here. We define that, all the coefficients. U is the discretized vector of u in time, and F are the, we can call them forcing terms that are shown on the right-hand side of this equation. Okay, so this is for constituting a matrix, and the next step that we gotta do to finally solve this equation and fully discretize this system. So if you remember, the first step was discretize in space, right? And then the next step is gonna be discretize in time. So I have it here. The next step is step 2, discretize in time. So solve the system of ODEs using time stepping or time marching methods. let's choose, so we have to choose one method for this. We can choose all the methods that we learned. We can choose like Rangakuta, we can choose Adam's method, all of them. But for now, I want to choose a simple one. Let's choose variable weighted Euler. Okay, I want to choose a variable weighted Euler method. So then the equation is going to be like this. The equation is going to be for du over dt at Tn plus theta. We are going to approximate that if you look at your notes and see what does a variable weighted method looks like, you will see that we are going to approximate it. This term is not going to be different than Euler. It's similar to Euler, but it's the remaining terms that might be different. So you're going to have u n plus 1. Let me write this all with capital to be consistent. So we have Tn plus theta, and then un plus 1 minus un over delta t. We can represent or approximate it like this in the Euler method. And this equals to the identity matrix, the two-dimensional identity matrix times these vectors, right? Un plus 1 minus un over delta t. And we need this identity matrix just to do the sum of the matrices, summations. So the second term is au, right? So I'm going to write it u at Tn plus theta. This can be approximated as theta. This is where we have the variable weighted method. So we are gonna impose it for this term, theta a un plus 1 plus 1 minus theta a un. Okay, this is for the second term here. And then the third term is f, right? The forcing term is sometimes called a forcing term. F at Tn plus theta, we just write it as Fn plus theta, okay? So now I can set and constitute the final set of equations. So I just write it du over dt as this. So let me write the equations that we had. We had du over dt plus a u equals to f, right? So these were the original equations. So let me write the approximation. So the approximation is going to be I un plus 1 minus un over delta t plus theta un plus 1 plus 1 minus theta. Why did I do this? I have to theta A 1 minus theta A un, right? Equals to f n plus theta. So I multiply everything by delta t, both left hand side and right hand side, and then factor un plus 1. So I'm going to have, the first one is just going to be I. The second one is going to be theta A delta t un plus 1 equals to, I take the un to the right hand side and factor that, so I'm going to have I minus one minus theta A delta t times un plus delta t f n plus theta. So this is going to be my final discretized system. So let me just show it like here. So this is my final discretized system, which is discretized both in time and in space. Okay. So let me, for the sake of argument, make this as, because these are vectors. We shouldn't forget that these are vectors that are discretized in space. And this is going to be my final set of equations. So this is also f, the vector. We shouldn't forget that. Okay, so this is not how you can write a code for that to solve it, but we have some choices. So let's see. If we want to choose theta equals to 1, then it might be a harder choice, because then we need to have a matrix equation. We will have a matrix equation that we need to solve. And we can do that by either iteration methods or other ways, because we don't know the value of un plus 1. So at each step we want to progress this, right? We want to progress this in time. And the other thing that we know is that the initial condition is 0. So that means that u at n is just 0. And 0 is a vector. And this is from the initial condition. It should be at step 1, right? Initial condition. Okay, so the first step, you are going to set this to, the whole thing to 0. You will have these forcing terms that are not 0, and then you are going to evolve it in time. Okay, but say if your theta is not 0, then you have this term on the right hand side, so it's going to be a matrix equation. It's going to be harder to solve. But if your theta is 0, it's explicit, and simply you can just solve it, because this term is going to be 0. And so you can simply find un vector, u1 vector, let's say in the second, u2 vector in the second step from this. And in the next steps, you already have un, so you have this term as well, and these two terms in the next steps, and you can simply solve that. So the choices that we have are as follows. So choices. theta equals to 0, then no matrix solution needed. And this is called explicit calculation, and it is order delta t. The second choice that we have is theta is 1. Then we need to solve the matrix equation, and it is called implicit calculation, and it is again order delta t. The other option that is kind of the advantage of using this method that we have is theta to be set as 1/2. This is called, as you might remember, Crank-Nicolson method. So Crank-Nicolson method. And this is also implicit and it is order delta t square. So that is the advantage of that the order of the accuracy for this is going to be higher if we choose theta equals to 1/2. So the last thing I want to note here is the stability criteria. So what is the stability criteria of the algorithm for theta equals to 0? And the criteria is if it's a conditional stability, and I just write it down so you see how that works. So if V delta x over D is greater than 2, then we require V squared over delta T over D to be smaller or equal to 2. And if V delta x over D is smaller than 2, then we require D delta T over delta x squared to be smaller or equal to 1/2. So this is the stability criteria for this algorithm and how it can be the stability of that could be reached or achieved. So it is a conditional stability. And I'm not going to go through how this can be found. This you can find it by using Taylor series and Taylor approximation. Okay. So this was the whole an example that wraps up this finite difference method. So you see in a real problem where you have both time and space, how we can discretize it, both of them together, all together. Okay, this problem is very general problem. And in the next sections, we are gonna follow. I'm gonna briefly introduce finite volume method, which is another method for solving these partial differential equations, another way of discretizing them by using another notion. And then we will briefly talk about the stability, a general way of stability for these numerical schemes, and that will wrap up the course. Okay, so let me just review what we did here. So we started with this full space-time discretization. So we wanted to discretize this method. We wanted to discretize this here, this partial differential equation, which is a transport partial differential equation, which we have both advection and diffusion term. And then we had these boundary conditions and this initial condition. So the first step was to discretize this in space. So we did that. In order to do so, I define different spatial finite difference approximations that we learned so far, different way of them that you can do that. And for time, we just chose this one, and we chose the simplest cases. So the first step that we are gonna just discretize in space. So this is the simplest case that we chose, but you can choose, of course, you can choose more difficult and more challenging cases. Then we came to this general equation, and then to be general and to see a general way of that, I just defined AI as the coefficient of ui minus 1, bi as the coefficient of ui, and ci as the coefficient of ui plus 1, and then the forcing terms on the right hand side, okay, or the source terms or the forcing term. And then we had to apply the boundary conditions because we are doing first space. So for the space we need boundary conditions. So for equation I equals to 2, which was the left boundary condition, we just did that, and we found u1 is set to u left, so we can just put it on the right hand side of this as a forcing term, okay, as a known, because we know this, we know u left and we know a2, so these are known, we put them on the right hand side, and these are unknown on the left hand side. And for equation I equals to n, we did the same thing, but because we had a different type of boundary condition, we had to use this technique or this trick, which is dominant extension, or sometimes you call this imaginary nodes, or you can this ghost cells if you have if you want to know in some of the more commonly used methods. And then we use this boundary condition to relate un plus 1, and then this is the equation we got for un plus 1. UN equation, okay? And the rest of the equations for I equals to 3 to n minus 1 are shown here. Then in this lecture, we use these equations and we constitute this general matrix here. And then we define the coefficients as A, the coefficients, and then we had the vector u, which is a discretized u in space. And then we finally got to this equation, which is a semi-discrete system, meaning that it is only discretized in space, and we haven't yet discretized it in time. So then we went to the second step where we discretized it in time. So we solved this system of ODE by using time stepping methods, and for that I used a variable weighted Euler method, which is shown here. And then we finally got to our final fully discretized system for the partial differential equation, both in time and in space, okay, with this initial condition. So we can now easily write a code, for example, in MATLAB or in Python or whatever you are more you are more comfortable with. You can just discretize this u first. For example, you can say n equals to 100 or 1,000 or 10,000, depending on the resolution that you are seeking. and then define this matrix A based on these coefficients that you have, and simply, for example, write a for loop to go in time. So from I equals to 1 to n plus 1, for example, n can be 1,000, 2,000, and just you can go in time and see how the solutions of this problem looks like. But there are two things. This is going to be very simple, like writing the code for that if you have theta is 0. So if theta is 0, you don't need any matrix solution. You can just explicitly solve this. Very easily you can march in time. But if theta is 1, then you need to solve a matrix equation. So you need to use other tricks, which we are not covering in this course, but you can look at them like iteration methods and other methods where you can use to kind of find and solve like nonlinear systems, or by trial and error, these kind of things. And then theta equals to 1/2 is where we have Crank-Nicolson method, and the good thing about it is that the order of the accuracy is increased. We are going to have a second order accurate scheme in time, order delta t square. And then I finally showed the stability criteria for the explicit method where theta is 0. This is going to be the conditional stability that we have. So if you have these criteria, then your computer code is going to be converged. You're going to have solutions. So if your v delta x d over is equal greater than 2, then your delta t that you need to choose should be in this order, right? So delta t should be smaller or equal to 2 times d over v squared. And if you choose that delta t, a small delta t, then your solution is going to converge. Otherwise, your solutions are going to blow up. Okay, so this was the kind of approach that we are going to take to solve these partial differential equations. And in the next lecture, I'm going to start working on the and introducing the finite volume methods briefly. Thank you very much, everyone.